happy that so many of you found the way to the Institute between 9 and 10 this morning. I hope you enjoyed the breakfast up there. Please, let's restart with the next lecture from Lucas.
Okay, so today, can you hear me okay? Yes? Okay. So today is my third lecture, and just to recap what we saw in the first lecture, we saw an algorithm that was capable of providing us numerical solutions to Schrödinger's equation in this very simple setting that we had a potential that had good symmetry, right? And then yesterday we had the opportunity to develop our own code to solve this problem. If your code is working, if you're getting the right answers, great. If not, tomorrow we still have some time to do this. Actually, tomorrow is reserved for the project that I'm going to explain today, but I have no problems answering questions of both projects tomorrow, okay? Just a quick show of hands. Who thinks their program is working okay? All right. Who thinks they need just more time? The problem is time, it's not difficulty. All right. The majority of people, okay. And who has, technical difficulties or difficulties with the physics of the problem? No one? Great. So if you put more time, then it should be okay. All right. And on my slides, I always leave my email. So if you have questions, please email me. Some people already did. Sorry, I didn't have time to reply to all emails yet, but I will do shortly, okay? Oh, and by the way, these slides are on the website, okay? So if you want to download and follow my lecture, you can do so. All right. So today, I'm going to talk about something that's a little bit more applied to atomic physics than the previous problem, and it's scattering. And I can see on your faces that you saw lots and lots of scattering these past few weeks. And I have to talk about it. Hopefully, I'll bring a fresh perspective, okay? There will be some math, but I want to focus with you guys on the physical aspects of scattering, okay? And the project will be about scattering. So this is your last chance if you want to ask questions about scattering in this school, all right? And if you don't have any questions, good. That means that you're following the material the past few weeks, okay? So please bear with me, okay? One last day of scattering. I'm going to leave a couple of references here. So pretty much all quantum mechanics textbooks, they cover scattering. Pick your favorite one. Griffiths does it, Sakurai does it. Pick your favorite quantum mechanics textbook. But recently, one of my students and I, we wrote a paper which is intended for an audience like you. Students, maybe at the end of the undergraduate course, beginning of the graduate course, where we introduce in a pedagogical way, in my opinion, a little bit more pedagogical than in standard quantum mechanics textbooks, two concepts: scattering length, that I think everybody knows what it is, and the effective range, which is something that's probably you heard a few times this week, right? So if you want a pedagogical introduction, please check this out, okay? And you're welcome to give me your feedback. You can say, oh, Lucas, this section here is not quite well explained. I didn't understand this. So if you have any questions, please let me know, okay? Right, so what's the usual setting of scattering theory, right? Setting up your scattering problem. Very far away from the region where scattering is going to happen, I have a free particle. And it's traveling towards this region where I'm going to have some potential that's going to be responsible for scattering, right? So very far away, I have a plane wave. Here, I chose my plane wave to be propagating in the z direction, okay? It's going to interact with this scattering center that's going to be close to the origin, okay? Something's going to happen there. And then if I look far away from the origin, what I'm going to see, the technical name of saying far away is the asymptotic behavior, right? The asymptotic behavior of the wave function. It's going to be an outgoing spherical wave, okay? And for this discussion, I'm going to assume that the scattering sense has a finite range. So scattering will occur close to the origin, but it will be a finite region very close to the origin. Is this new to you? Not at all, right? Okay. So I already said that the potential is finite ranged. I'm going to put one more restriction, that is, it is spherically symmetric. That's going to make our problem easier, okay? And then my asymptotic wave function, my wave function, if I look far away from the origin, it's going to be that plane wave that was coming, my initial state, and the spherical wave with this weight here that's going to characterize how much it was scattered, and it's called the scattering amplitude, okay? Inside of the region of the potential, so I'm going to say that my potential has some range big R, I want to solve Schrödinger's equation, okay? And how we do that, this is a three-dimensional equation. Well, we know that the potential is spherically symmetric. I can propose a separable solution in terms of a radial wave function, a function that depends only on the distance r. And I know that since the potential is spherically symmetric, my solution is invariant under rotations. The angular solution are the spherical harmonics, right? So you plug that into Schrödinger's equation. You write the Laplacian in spherical coordinates. You get one equation for the angular part, another one for the radial. And the radial equation looks ugly, right? Because if you ever wrote down the Laplacian operator in spherical coordinates, it's a big mess, right? But if you're clever, you can do this change of variables here, where instead of working with the radial part of the wave function, you work with another function that's, if you divide it by r, then you get the radial wave function, the full radial wave function. And why do we do this change of variables? Is because then you eliminate the first derivative term in the equation that you want to solve. You just have a second derivative. So it looks like this. And this term here, the centrifugal barrier, I'm going to talk later about it, but it also comes from the expression of the Laplacian. So far, everything okay? You already know this, right? Okay. So the wave function must be finite at the origin. Since I I did this change of variables, I would have problems if this r here was 0, right? I would have a 0 in the denominator. So what's the boundary condition that I have to put in this equation? I must require that it's 0 at the origin so that I don't have any problems and the radial wave function is finite, okay? Outside of the range of the potential, meaning v equals 0 outside of the range of the potential, I have a differential equation with solutions given by a linear combination of spherical Bessel functions of the first kind and second kind. It's a second order differential equation, so I have two constants that I need to determine. Right? Something new here? No, right? Okay. So I want to divide my problem into angular momentum components. It's what's called partial wave expansion. So the first thing is I have this incoming plane wave, right? And then if I want to decompose my incoming plane wave, which is e to the I kz, z I can write it as r cosine theta, I find out that if I divide it in a sum of components with different angular momenta, the plane wave has an infinite number, has all the possible values of the angular momentum, all values of L, okay? This is called Rayleigh's expansion, okay? It's just a mathematical expansion of this function here. As I said, when we're looking at scattering, we always want to look at what happens far from the origin, okay? So let's look at the asymptotic behavior of this, meaning that we have to know how this Bessel function here behaves for large arguments. And what we get is the following here. So my plane wave has an infinite number of partial waves. And far away from the origin, it's a combination of an outgoing spherical wave and an incoming spherical wave. Okay? So this is what happens with the free particle that's coming towards the scattering center. Okay? But we want our wave function for all space. We don't want just our wave function for the free particle that's going towards the origin, right? So motivated by this, we write the solution of our wave function for every possible value of r, which is the combination of the incoming plane wave and whatever happened inside the scattering center. We write it like this, okay? Just by comparing these expressions here. And if I plug in that reduced radial wave function that I derived in this slide here, if I plug that in here, what do I get? I get this asymptotic behavior here, okay? And now I want to compare what's happening here with here, okay? With those two expressions. So I have two coefficients that I need to determine in this asymptotic behavior of my full wave function, my wave function that encompasses everything. Well, if I take them to be equal and equal to half, I get exactly the same equation as the one for a plane wave. This shouldn't be surprising, because if I'm choosing this very special combination of coefficients, it's really the free particle solution, okay? So what I'm saying is there was an incoming plane wave, the scattering center, and then there was an outcoming plane wave as well. So V must be equal to 0. Nothing happened there. But if I choose slightly different coefficients, that's equivalent to changing the solution, comparing with the plane wave, and then putting weights to this incoming and outgoing spherical waves, right? So these coefficients here somehow are controlling, are telling me what happened inside that scattering region, right? And what's important, really, it's the proportion, the ratio between those coefficients. They're telling me something about the scattering length, that something about the scattering that took place in that region, okay? So these coefficients are what quantify this impact of scattering. Is this okay? Is this new to you? No. All right. So I'm going to define this quantity here, the ratio of those components to these two coefficients, which is what has physical meaning, and that's going to be this exponential, this complex exponential of those quantities that I'm going to call delta. Formally, what would I have to do? I would have to take this and substitute in all those expressions and expansions to really show you what's going on with those phase shifts. But I know that you guys saw this over and over the past few weeks. So I'm assuming that you all did this at some point. Is that correct? Okay, good. So I want to talk to you about the physical meaning, the interpretation of phase shifts, okay? So these quantities here, they are telling us that the most that can happen with the wave function after being scattered, it was a change in phase, because this scattering process conserves probability, right? So if you're conserving the probability of your wave function, at most what can happen to it is a difference in phase, right, when scattering took place. And the scattering, the phase shift becomes simply the difference between the phases of your solution. If you had some scattering going on, if V was different than 0, close to the origin, compared to the free particle case. Okay, so that's the physical interpretation. V equals 0, there's no phase shift, because there's no difference in phase. Whatever came in, came out the same way, right? However, if you have some potential that's different than 0, the radial solution inside this range of the potential is going to depend on the details of the potential, right? You give me one potential, I'm going to tell you what's the solution inside the range. But outside, it's always the same, because outside, V equals 0, right? So we know what's the solution outside the range of the potential, no matter what's the functional form of it, all right? So what this is telling us is whatever happens inside here, inside the range of the potential, is going to dictate the phase shift outside. And we can think the other way around. If we look at what's going on outside of the range of the potential, we can infer what's going on inside, okay? Good. And what's the advantage of this formulation of phase shifts is we took scattering and we substituted computing all those quantities by computing just one quantity, and it's real. It's a phase shift. Of course, it depends on the angular momentum components that you're considering and of the energy of your incoming particle. Okay. Have you seen this picture before? Yes, right? So what's going on here? The dotted dashed line is the free particle solution, so it will be a solution that you get if you set V equals 0 in your equation. And if you put an attractive potential near the origin, what's going to happen? The wave function will be pulled towards the origin, right? It's an attractive. You want the particle to be closer to the origin. And this will have a different form here inside this range R of the potential. But outside of the potential, the two solutions will be the same. There is just going to be a difference in phase, right? And this distance here will be given by this phase. The free solution is always ahead of the solution with some attractive potential. So in this case, we say that the phase shift is positive because the free solution is ahead. Okay? Questions? Yes, Sheila?
Lucas, did you put the potential at that point there? Because I can see that waves start at the same point. The dashed dotted and the full line, the solid line, they start at the same point, right? Because I think that if it was just shifted, maybe one should be... the location, the region.
The boundary condition is the same for both, right? For both cases, you must have that this reduced wave function equals to 0 at 0, okay? But what happens is, if you do the free particle case, V equals 0, okay? You just get this sign here, okay? So that's what happens. Now, let's put something that's attractive. Here, I put a spherical well, all right? It has some depth here and some range R. And then it's going to, it's an attraction, right? So the particle will be closer to the origin, right? So this is what's happening here, okay? As you can see, it is located closer to the origin if you compare to the free particle solution. So
I will ask
I'm
you
not
later.
sure. You can ask me later, but I mean, this thing is doing what it's supposed to do.
Yeah, okay. I just, maybe I am confused.
Okay.
I don't want to late everybody because of this, okay?
Okay, but if other people have questions about this, we can cover this.
What about the maximum value inside this spherical well? I understand the shift. You have a...
I understand the shift.
Yes.
I know that you have a shift because you have an attractive potential, but about the maximum value of this
So
oscillation,
you want it to be a little bit higher, right?
Yeah, no. I asked and while I was asking, I got what is happening.
So one thing that I've never careful when I'm doing this is the normalization, because as you see, there's one way to work within this scattering formalism where you can get away without computing the normalization, right? So we will see during this lecture how this works. So after I get rid of normalization, if this is still a question, please do ask me, okay? But I'm lazy. I never want to compute the normalization if I can get away without it. Okay? All right. So this was for an attractive potential. You can also have the same thing for a repulsive potential. For a repulsive potential, again, the dashed dotted line is the free particle solution. If I put something that's repulsive, it wants to push away my particle from the origin, right? So the wave function gets pushed. So now the wave function with the potential is ahead of my free particle solution. Then I'm going to define this as a negative phase shift. Okay, it's just the opposite situation to the previous figure. Okay. All right. So far we talked about this partial wave expansion for an arbitrary angular momentum. Of course, those figures I showed you, I had to pick one component. Of course, I picked L equals 0 because it's the one that's going to be interesting for us. But we want to work in these low energy limits. It's very convenient for cold atoms. It's not the only situation where it's convenient. Sometimes in nuclear physics, it's also convenient. Okay. So what do we need to do in this setting? We have our Schrödinger equation for some partial wave L, okay? And it has all the features we talked about. But if you look at these terms here, it's like you have the potential that could be attractive or repulsive, as we just saw. But we also have the centrifugal barrier, right? And this is a positive number, so it's repulsive. Whenever you get close to the origin, so if you put a small number here or 0, this term is going to get very large. And it's going to increase as L squared when you go to higher partial waves, higher numbers of L. So you have this really repulsive thing close to the origin, okay? If we're talking about low energy physics, my energy, it's pretty small compared to all the other typical energy quantities in my problem. The particle doesn't have enough energy to overcome this barrier, the centrifugal barrier. So for low energy processes, this particle cannot go over this. But luckily for L equals 0, the barrier goes away. And you can, and that's going to be the most important partial wave when we're dealing with low energy phenomena, okay? And you all know another name for L equals 0 is S wave. So that's what we are saying when you're saying that we're doing S wave scattering, all right? The radial wave function, you can write it for the L equals 0 components. You have your phase shifts. You substitute what's the Bessel function of the first kind for L equals 0, the Bessel function of the second kind for L equals 0, and you get this nice expression here for the behavior of your radial wave function with the phase shift here. So here it becomes pretty clear why it's called a phase shift. It's a phase inside the sign. This is boring, right? So you saw this like 1,000 times so far, right? Okay. But now we're coming to an equation that's really easy to solve. So in this low energy limit, if you consider the solution outside of the range of the potential, so my potential for large distances goes away, it's 0. I'm looking at low energy, so it's S wave, L equals 0, and you set the energy close to 0. That's my favorite Schrödinger equation to solve, right? It doesn't get any simpler than that. The second derivative is 0, so the solution is just a straight line, okay? And it's a second-order equation. I have two constants that I need to determine. I'm going to write like this because I already know the answer. That's why I'm writing it like this. So, as I said before, I want to take the normalization problem to go away. All right? So I don't want to calculate this normalization. What's one possible way of doing this is, you've done this 1,000 times in quantum mechanics problems. You have a potential that's discontinuous. It's continuous in one range, in one interval, space interval, and then it changes value when you go to the next. So what you do almost instantaneously, you match the wave function and the first derivative, right? I'm also going to do this here, but I'm going to do their ratio. Because if I do their ratio, the normalization is in front of it, it's a constant, and it's going to drop. I don't know if you heard this term before, calling it a logarithm derivative. Probably if it's the first time and you hear this name, you're confused because you said, oh, I must be sleeping. Where the hell a log came from, right? But it's because of this. If you take the derivative of a log of a wave function, you get the derivative of the wave function divided of a function divided by the function. Okay, so this is the origin of the name. There's no log involved, but people will often say this when they mean, oh, the derivative of something divided by the something, okay? And if I do this with this simple line equation here, I get this. But in the previous slide, I wrote the radial function, reduced radial function, in terms of the phase shifts. So I can also take the logarithm derivative of this and match to what I just saw. If I do this, I get this equality here, and then I'm ready to take the low energy limits. If I take the low energy limits, this is something that you saw 3,000 times now during this course, which is the very definition of the scattering length. This is telling me that all the behavior encoded in these phase shifts in these very special limits, this is the zero energy limits, the limit where my energy is going to zero, is described by just one number. And this number is the scattering length, right? So what we've done so far, we reduced the scattering problem, the whole scattering problem, to computing phase shifts. Then we argued, oh, for low energy phenomena, just L equals 0 as wave dominates. And now we are saying that in this very special limit, a single number has all the information we need about scattering. Scattering length, the name suggests it has dimensions of length, but that could be misleading in the sense that it could differ by orders of magnitude from the range of your potential. You may have one potential that has this range, and the scattering length can differ by many, many orders of magnitude. And as you know, it can also be infinite, okay? But what if we want to give a geometrical interpretation to the scattering length? I'm going to write that line solution that I got in the last slide, the one from the second derivative of the reduced wave function equals to 0. I'm going to write it like this. Because if I do this, I can give a simple geometric interpretation to scattering. It will be, the scattering length will be the point where my U crosses the R-axis, okay? Because when this happens, let me show you a picture. When this happens, I get 1 minus 1, I get 0, okay? So the first example that I'm giving here is if you have an attractive potential, it's going to have some solution that depends on the potential here up to its range, but outside of it, it's going to be a straight line. And this straight line will always go up, because if A is negative, this thing is positive, then it goes up, all right? Then the scattering length becomes, if I extrapolate it and see where it hits the R-axis. That's the scattering length, and that's why it's negative, because it crosses the R-axis at a negative position. Is it the first time you're seeing this picture? Yes? Yes, I got something fresh for you for scattering. Okay, so this is the way that I and other people interpret scattering, the scattering length geometrically. Yes. This is called spherical well. So it's a potential that's constant inside of the range R of the close to the origin, and outside of it is 0, okay? And it's attractive. Oh, I'm happy. There's something new about scattering. Great. All right. So can you see this geometrical interpretation? All right. And in this simple example, you can see that A, in this case, is larger than the range of the potential. And depending on this angular, the inclination, the slope of this straight line, I could make it much bigger, right? So I could do it so it intercepts the function here, okay?
Here, the wave function is coming from the left, and then it is scattered by the potential in the R range, and then the wave function blocks up.
So what's going on is R is a distance, so it's always going to be positive. So if you want to write the reduced wave function in a physical system, in a physical way, I should plot only this part of the graph. I should stop here and plot only this. But I want to give a geometrical interpretation to negative scattering lengths, okay? And what is a negative scattering length? It is negative because this thing here is never going to cross the R-axis. Why is never going to cross? Because I have 1 minus, this thing is minus, so I get a plus. It's just going to grow with R, all right? So it's not going to intercept R in the positive R's. But what I can do is, I look at the wave function outside of the range of the potential, and I extrapolate it. And then I see where it crosses the R-axis. Then I'm going to say, oh, the scattering length is this large, this big, with a minus sign. Does that make sense? All right, good. Probably I should have showed you the next slide first, but this happens when you have some attractive potential that's not strong enough to produce a bound state. So this thing is not a bound state. This thing here has positive energy, okay? What happens if I increase a little bit the depth of my, my potential, okay? If I increase, I make a well that's deeper than the one before, what can I have? Oh, the wave function crosses now the R-axis in the positive side. So that's a positive scattering length, okay? And the point where it crosses here is the scattering length, because if I set R equals to A here, I get a 0, okay? So for an attractive potential, positive scattering lengths correspond to bound states. Is this new information for you, or no? Kind of? Yes.
How general is this geometrical interpretation?
How?
General.
General.
Yeah. We can apply
As
it
general
to.
as whatever low energy scattering theory works.
Okay, thank you.
Mm-hmm. All right. These are for positive potentials. I can also have this for a repulsive potential. So here I'm putting a repulsive potential close to the origin, okay? And then for repulsive potentials, you always get positive A's, because when you extrapolate this thing here, it's always going to hit your R-axis on the positive side, okay? So, just to recall, negative scattering lengths, no bound states. Positive scattering lengths, if it's attractive, bound state. If it's repulsive, always positive, okay? Yes.
But if you go to the bound state, I mean,
To the bound state, okay.
in order have this positive scattering length, you need to take out energy from your system. I mean, that's not something that is going to happen if you don't have an effect over the system. I mean.
So scattering, the scattering that I'm dealing here conserves the total energy, okay? So here you have a bound state in the sense that the energy of your system is negative. That's why you were able to confine your particle in a region of space.
Yeah, but
this discussion...
The distance continued increasing, so how is bound state?
Okay. Remember that this is the reduced wave function. I still need to divide by r to get the radial function. And r is going to increase pretty fast, okay? And what I want to say is this is a general discussion with pictures. I prepared an example that we're going to see in practice how continue and bound states work. And then you let me know if it's clear from the example. If not, we can go back to this. But I'm just showing pictures and saying things, but we are going to do like a formal example. Okay? Good. All right. So far, I only talked about one particle coming from infinity and going through the origin, being scattered, and then it moves away. But the problem that we're interested most of the time is I have two particles, okay? They are going to interact through a two-body potential, okay? And I want to describe scattering in this scenario. Either they're going to scatter and each goes their own way, that would be a positive energy, or they're going to form a bound state, that's going to be a negative energy. So this is the physical situation that I'm more interested at than just one particle, okay? And with a few modifications, I mean just one modification, we can use all the results we derived from this theory and apply it to this two-body system, okay? And what we need to do is you write down your Hamiltonian for a two-particle system. You have the kinetic energy of the first and second particle, and they're interacting through some potential. I'm going to assume that this potential is spherically symmetric, only depends on the distance r between the particles. And I'm going to define center of mass coordinates and relative coordinates, okay? Where this m here is the sum of the two masses, okay? If I do this, I can rewrite my two-body Hamiltonian in a Hamiltonian that depends on the center of mass and the relative coordinates. The center of mass is trivial. It's just going to be a plane wave propagating constant energy. Constant energy is not going to add anything to my problem. But what's interesting, it's the relative motion of the particles. This is non-trivial. This is the thing that I want to solve. And if you look at this, this is exactly the same equation that we were solving before for the one particle problem. But the only modification that I did was I changed the mass for the reduced mass, right? It's just like what we would do for the hydrogen atom. Okay? Okay? All right. So I want to do a concrete example with you, which is the spherically symmetric finite well, spherical well for brevity, okay? And what does this potential look like? Well, it's attractive up to a range R, and outside of it, it's 0, all right? I could write just like I did on the board here, but I want to write it a little bit differently because I want to put a dimensionless parameter in front of my value here. And we saw in the first lecture that h bar squared divided by mr squared, this has units of energy. So this means that this V0 that I define is dimensionless, okay? So it's just a fancy way of writing this. And it's attractive, okay? So I'm just going to consider this parameter being positive because I put this minus sign in front of it, right? R controls the range of the well, and this V0 controls the depth of the well. Increasing V0, I'm going to make a deeper well, okay? And if I have a really shallow well, so imagine that I have just a potential that's really close to 0 here. Probably this won't be enough attraction to form a bound state, all right? So I need to make a deeper well if I want to observe bound states. So I could start from a situation where I have only scattering states, that means positive energy, or if I increase the attraction, it might be just enough to produce a bound state, all right? Let's start with the scattering states, the positive energy states, and then we need to solve this equation here. So far, so good? All right. And you haven't seen this example before in the school? Or you have? You have? In the school? No. All right, there's some debate if this has been done or not. This will be done again. Okay.
Hello.
Yeah.
Yeah. For S wave, like L equal to 0, not L equal to 1, like P wave.
So it's that discussion that I did around the
That is-
centrifugal barrier,
Yeah.
right? So if you're really going to the zero energy limit, there's this huge repulsion close to the origin, right? So your particle would need more energy than it has to overcome this barrier because it's pretty close to 0. So it's like if you're trying to jump over a really high wall. You really have to have a lot of energy to do that. But we are not working this limit. We're working this other limit where energies are small, really close to 0. That's the regime that's relevant for cold atoms and nuclear structure and things like that. So partial waves are important if you increase your energy in this higher partial waves. In this limit that we are working with, not so much.
Okay.
Okay. All right. More questions? Okay. So this is the equation that we want to solve. And this V here has two different forms inside or outside the range of the potential. Okay. So if I write down explicitly the two cases, for the region inside of the well, where I have this constant potential, I have this equation here, and outside of the well, I have V equals 0. So I have a free particle type of equation. Here I defined k square, the usual k square, just putting here the reduced mass, and I defined this other k0, which is related to the parameters of the potential. It's related to the depth of the potential and its range, okay? But it's just a matter of defining my constants. And I defined those such that K0 has the correct wave vector units, okay? Can everybody see that these equations are exactly the same that I wrote in the previous slide? Okay, good. So let's look first at inside this region, right? Inside this region, you know what the solutions are. You have sine and cosine. The argument here is going to be a little bit different from what you're used to, but that's because I defined this thing here that I could call, I don't know, capital K square, right? So it would be capital K times R, capital K times R. It's like this because I defined my quantities like this. As I said before, U is not the radial wave function. It's the reduced wave function. We still need to divide it by R to get the radial wave function. So remember that this has problems at the origin, leading to the boundary condition that at the origin, I require it to be 0, so I don't have problems here. I don't have divergences. And if I impose this boundary condition in the solution here, I get that b equals 0. I only have sign types of solutions. Okay? Outside of the range of the potential. That's what we did in the beginning of the lecture, right? It's related to the phase shifts. And I wrote it like this because it's going to be convenient for us. But it's pretty much the thing that we saw in the beginning of the lecture, all right? And then I'm going to require that the first derivative and the function to be continuous at r equals big R, okay? So this is a very nice calculus exercise. You get to derive sine here and divide by sine. Here you get to define sine and cosine, and you get this ugly expression here. And this, after a few manipulations, that reference that I gave in the beginning of the class, that archive that I said, I do it step by step if you want to follow, okay? But what's very nice about this potential is you get an exact, although ugly, expression for the phase shifts, okay? So this is a nice example where you can get analytically the S-wave phase shifts as a function of K, the energy. All right? Is this new for you, or have you seen this before? Somebody talk to me. It's either new or old. New. Good. All right. But what we want to do, the focus of this lecture is to calculate the scattering length, okay? So how do we calculate the scattering length? Well, we saw that we had this expression here that's related K cotangent of the phase shift to the scattering length, and I was throwing away orders, terms with orders of K squared and higher orders, all right? So I go back to that ugly equation there, and I want to take the limit K going to 0, all right? The left side, it's easy to take this limit. I just set K's here to 0, and I get this left side here, all right? Can everyone see that? Okay. On the right side, it's a little bit more complicated, because what I want is I want factors of K cotangents of delta, because when I take the limit of this, I get minus 1 over A. That's my strategy here, all right? And I have a bunch of cosines and sines here. I'm doing my, this result here is good up to order of K squared. I'm throwing away K squared and higher order terms. So I have to expand cosine and sine up to the same order, right? Cosine up to this order is going to be 1. Sine is going to be KR. I do this on this right side here. For example, here I get KR times cotangents of delta. When I take the limit, I'm going to get the scattering length. So I get this thing here on the right side. Can everyone see why that works? All right. And then I can solve for the scattering length using this. I get this expression here for the scattering length that relates scattering length to the range of the potential and its depth. So if you tell me what's the range of your potential and what's the depth, I can tell you analytically what is the scattering length, all right? So give me the potential, I tell you what's the scattering length. That's what this equation is telling us. Now, it has a tangent here, like tangent of x divided by x. This diverges at some values. So if you plot this, you get something like this picture here. Have you seen something like this during the school? Yes. All right. So this is what's happening when you solve explicitly some model, okay? And you could observe this experimentally, for example, using Feshbach resonances or something like that, all right? But that's the physical origin of this, all right? Okay, for some values, the tangent here diverges. And we have the scattering length that starts at 0. So if I have a really, this axis here is related to the depth of the well, okay? So I start with a really shallow well, my scattering length is 0. I start to increase the depth of the well, it's going to get negative, but larger. It's going to diverge up to minus infinity. At some point, it's going to be plus infinity, so it's going to flip signs, and then it's going to start to get smaller, and then it's going to repeat this, all right? So that's what's going on. We can see this from the mathematical structure of this. But we can ask ourselves, what's the physical origin? I mean, of course, tangent of x diverges, but physically, what's going on in my system that makes this thing diverge for these values? Do you know the answer? Bound states, right? Whenever a bound state appears, I'm going to have this divergence. So let's see how this works. Okay? So far, I did all my calculations with positive energy, scattering states. Now I want to do bound states, negative energies. I could do all the calculations again, and at the end, you would all be sleeping, right? But I'm going to use a trick. I'm going to do this substitution here. Whatever I had k before, I'm going to write I kappa. Why am I going to do this? My energies are proportional to k squared. If I substitute this by I kappa, what do I get? Minus kappa squared. So by doing this substitution, I avoid doing all the math, and I can just look at my bound states, because now my energy is going to be negative, all right? Do you see why this works? Okay. So I had my previous result was sine of k0 squared plus k squared. Now I have I squared. This becomes minus kappa squared. So this is the solution for the reduced wave function inside of the well. And outside, I have a vanishing wave function because it's a bound state, right? Has to go to 0 outside of the well. I do all the business again of matching the first derivative and the function, the ratio of the two. I get this ugly equation here, and I rearrange a little bit the terms, and I get this equation here, which is transcendental, which means that I cannot solve it analytically. Numerically, it would be really easy. Pretty much if you open a numerical calculus textbook, you find lots of methods that give you roots of equations like this, right? And this equation is telling me that for some values of kappa, I'm going to have these bound states are allowed by my potential, okay? Okay, we can't solve this analytically, but if we look at it, we can get some conclusions, have some conclusions that are going to help you with our discussion here. This term here is always positive. Why is it always positive? My energy is negative, but I define it such that E equals minus kappa squared. So kappa squared is positive. If I remove something that's positive from this, this is fine because the K0, as I define, depends on those parameters of the potential. The kappa here divided is positive, so I get the conclusion that this thing here is always positive. If I want this equation to hold, if this thing is always positive, I need this thing to be negative. Otherwise, I couldn't get a 0 here, right? So we require that this thing is negative if we want to have one solution or solutions, plural. We could have a situation where we have more than one bound state. Okay, I want my tangent to be negative, so this argument here must be between pi over 2 and pi, and the tangent has a period of pi. I can have n pi of this to get my solutions, all right? This thing here is always positive, as we discussed, so I can only have this n to be 0, 1, 2, and so on. Otherwise, this won't be satisfied, okay? And the first state occurs when I have n equal to 0. All right? So for n equals 0, I have this inequality here. It's a bunch of inequalities, but I promise at the end we're going to get something that's useful, right? As I said, kappa squared is positive, so if I remove from K0 is always going to be larger than this. And then at the end, if I substitute the value of K0 in terms of our potential parameters, the depth and the range, I get this simple inequality here that has a lot of physical meaning. This thing here is telling us that my V0 has to be above a certain threshold value. I mean, it has to be deeper. My potential has to be deeper than some critical value if I want to observe a bound state. All right? So that's the conclusion. I start with a very shallow well, no bound states. I keep increasing the depth. At some point, one bound state appears. Of course, if I kept doing this business, I would see a second bound state, third, and so on. All right? It so happens that this value here is exactly where the scattering length was diverging. The second bound state appears when the scattering length is diverging here. The third one here, okay? So a diverging scattering length occurs whenever I have the creation, I mean my potential admits a new bound state. So that's what's physically going on in my system. Scattering length diverges, new bound state. Does that make sense? Is this new information or 1 over square root of 2 new information, 1 over square root of 2 old information? More or less. All right.
How can you get an intuitive physical picture of this? Like when you have bound states, at the energy of the bound states, there is a scattering resonance.
So what's going on is whenever you create a new bound state, so let's picture this potential getting deeper and deeper. Scattering states, the bound state is created for some critical value. What's the energy of this bound state? At this very point here. 0, right? It's just barely enough to create a bound state, right? Of course, if I keep increasing the depth of my potential, it's going to have some negative energy, but at the very threshold, I'm in the limiting case, it's 0, okay? So that's what an infinite scattering length is. You just created a bound state in your system. And it's really the limiting case. We saw those geometrical interpretations, right, of the scattering length. That would be equivalent to a wave function, a reduced radial wave function, that does something like this. Remember, it's... So my wave function would go to 1, meaning that the particles see their interaction infinitely far apart. That's what an infinite scattering length is, all right? And it's infinite because it doesn't matter which way I extrapolate this, it's never going to cross the r-axis. So somehow this interaction is tuned to a value that's so special, specific, that you create a bound state, but is as if the particles see each other from very, very large distances. That would be the physical intuition. Does that make sense?
Yeah, thank you.
And that's why it corresponds to an increase in the cross-section. Because if you can see, if I'm here and I can see somebody, I don't know, at the hotel, I mean, the interaction is of a length scale really large. Okay? All right, still have time. So to summarize this first part of the lecture, we started with scattering, Schrödinger's equation. We plugged in a spherically symmetric potential that was finite range. We proposed a separate solution. Then we get an equation for the radial wave function. We said, oh, okay, if we do this clever substitution, I get this equation here with the boundary condition that must be 0 at the origin. Then we said, oh, but we don't want to do scattering in general. We want this very special limit of low energies. Then we argued that for this special limit, the most important partial wave is L equals 0. We took the low energy limit, that means that K goes to 0. We get this much more simplified equation that we need to solve, with V being of some form inside of the range of the potential, but outside it's 0, okay? Because it's finite range. Okay, so this is the summary. Now it's the project that I'm proposing for you to develop your own code. And the project is computing the scattering length numerically. I just worked out an example where we have an analytical solution, but that's kind of the exception. For most potentials, you cannot write an analytical solution for the scattering length. Then it's a good idea to compute them numerically, okay? And it's apparent now that for the first lecture and for this lecture, I chose, and I showed you analytical examples so that you have something to compare your code with, right? So you're developing your code, you know what you should get. This helps you develop, find out the bugs in your code. But this one here would be really important, special, if you want to consider some other potentials that don't have analytical solutions. So if you have a code that works for the spherical well, you can change the shape of the potential and then use it to calculate for other potentials that may or may not have analytical solutions. Okay? So what's the key? The first step is we need this function U of r inside the range of the potential. So we need to solve this equation here numerically. And if you recall the first lecture and the code that you've been working on, this is exactly the same equation that we were solving. It's even easier because now the energy is 0. So you don't have that problem that you had in the first project of, I need to solve for the wave function and for the energy at the same time. Here, I just need to do once. I know the energy. The energy is 0, okay? So I just need the wave function. And we are going to do the same thing we did in the first lecture. That is, recall, I wrote down 2 Taylor series, right? And by combining them, their difference or sum, they gave expressions for the first numerical derivative and second numerical derivative, right? And I plugged that into Schrödinger's equation, this equation here. And then we got this scheme here that if I know 2 points, I can calculate the third one, right? If I know 2 consecutive points, I can calculate the third one. Notice, this is much simpler than the one before because now I don't have the energy, I just have the potential. And the potential is going to have some value inside of the range of the potential. It's going to be some non-zero value, but it's going to be 0 outside, okay? So from the technical aspect, it's much easier than the first project. The complication now is the physics. This has much more physics content than the first one. Okay? All right, so what would be an algorithm to do this, to find the reduced wave function inside of the range of the potential? You take as input of your code the number of points or the spacing delta r that you want to solve your problem, okay? And you need the parameters related to the potential, its depth and its range. Oh, and something that I didn't say is I'm writing all the h bars and m's here. You should work in dimensionless units like we talked about in the first lecture. That makes things much easier, okay? All right, boundary condition. I said a lot of times there, to avoid any divergences at the origin, set your u to be 0 at the origin, okay? How about the next point? The next point has some non-zero value. Pick whatever you want. We are not worried about the normalization. The normalization is going to drop when we divide the numerical derivative by the function, right? So I'm picking 1. You can pick 0.1. You can pick whatever constant that works, right? And then you use this to compute your wave function, your reduced rate of wave function for all the space. And you do this for the range of the potential. Actually, I'm asking you to do a little bit more. go up to the range of the potential and do one more point. Do also this one. Okay? In a second, it will be clear why I'm asking you to do one more point. We know from the analytical solution outside of the range of the potential, remember this thing here that we were talking about, we know that this gives us the scattering length. It's encoded in the behavior of the wave function outside of the range of the potential. If I consider the logarithm derivative, I get this. So outside of the range of the potential, it's true that if I do this ratio here, I get 1 over r minus a, okay? But you can also compute this radial wave function inside of the range of your potential, in this region here, okay? So you start at 0, and you compute your reduced wave function up to this point here, okay? And then what's the numerical derivative at this point r here? What's the numerical derivative here? From that numerical expression that we wrote before, it's the value of the function on the next point minus the value of the function in the previous point. So hopefully now it's apparent why I ask you to go over 1 point, because you're going to need these 2 points here to calculate the numerical derivative, okay? Once you did that, if I match this to this divided by the numerical value, I get this expression here for the scattering length in terms of the range of our potential, okay? And it's going to depend only on 3 values from your numerical solution. You just need 3 values. You need these 3 here, okay? And from that, you can compute the scattering length. Of course, you need to solve the equation in the whole range, because you're going to start at 0. Your boundary condition is at 0. But then you keep going, and then these 3 points are going to be enough to calculate your scattering length. Does that make sense? Can you see this happen in your program? Okay. So this is the project that I'm proposing for tomorrow, which is write a program that does this stuff that we've been discussing in this lecture. And then the inputs of your program should be the depth and range of the potential. You should give that to your program. First step is finding the reduced wave function in this fashion that I just said. And then you can use it to calculate the scattering length. As we saw, you just need 3 points, and then you can calculate the scattering length, right? My suggestion is work in dimensionless units, as we did in the first project. And in these units, make them so that the range of your potential is fixed at 1. So in your program, you can say that this is r equals 1, okay, in this reduced units, okay? And then I'm asking you to vary the depth of your well, so the V0, the one that controls the depth of the well, and here I put 5 values of the scattering length, but these are arbitrary. You can do as many as you want. It's interesting to do 1 positive, 1 negative, and infinite to see what's going on, okay? And then you have this analytical expression that I wrote to compare your results with and see if your code is working, right? You get the scattering length, but you also get this reduced radial wave function. And I'm asking you to plot this for 3 cases. Plot for a negative scattering length, a positive one, and when it diverges to see what's going on with the radial wave function, okay? And as always, I leave some questions for you to think about it. What are examples of other potentials that can be solved with this method, okay? And in the last slides, I leave the results that I get for V0 with 3 decimal places, okay? So depending on the precision that you want, you probably need more decimal places here, especially for unitarity. Well, that's it. can you see this project working out? Can you see, do you imagine yourself writing this program, or do you anticipate some difficulties? I liked that I got a positive over there. Okay, so do you have any questions? Yes.
Yeah, the second.
Microphone.
Why are you taking the second point as 1? I mean, the initial 2 points. U0 is 0, that I understand,
Yes.
to avoid the divergence. But what U1 is 1?
Okay. So we're dealing with an attractive potential, right? And we started our wave function as being 0 here, right? What are my choices? My choices would be 0 or a number different than 0. We can put the problem as this, right? If my next point is 0, let's see what happens. I have 0, 0, 0. It's going to be 0 everywhere, okay? So that's probably not the correct choice for my first point. Let's put a number different than 0. It could be positive or negative, okay? If you run your algorithm, you see that it's going to do something. You're going to get a solution that's different from 0 everywhere, okay? But then you say, oh, Lucas, I wanted to pick -1 here, okay? You said, no, my U1 is going to be -1. Then I'm going to flip the sign of the scattering length. No, you're not, because the normalization is going to drop. When you do this, if you have a minus here and a minus here, it's going to drop. So you can pretty much put any non-zero value here that's going to work. I chose 1 because I chose 1. It could be 0.1, could be -0.1, could be anything.
So I could have used delta R.
Delta R. Okay. Perfect, fine choice, yes. Schrödinger's equation is linear. If you have a solution and you have a solution multiplied by a constant, they're both going to be solutions. We don't care about the normalization because we're going to do this ratio, and then it's going to drop.
Okay. Thanks.
More questions? Early lunch then? No, question.
Numerically, what would be the difficulty if we, instead of a square well, we consider a smooth edge of the potential?
Numerically, it would be exactly the same thing. Okay, so you say, oh, I don't want to do this. I want to do this, for example, right? Numerically, it wouldn't change much. Analytically, you can imagine that for just a very few select choices, this thing is going to have analytical solutions. The only one that comes to mind, if you want the scattering length over all the range, is a potential that's like this. Some parameter here. So 1 over cosine, hyperbolic cosine squared. This one has analytical solutions. And of course, this looks like something like this. It's called the modified Posh-Teller potential, if you want to look it up.
Thank you.
Mm-hmm. More questions? It has a very beautiful name. Modified Posh-Teller potential. There's also the Posh-Teller potential. Probably there are some solutions for it as well. Done? All right. Thank you.
I just sent the email to announce at 3:30 at the end of Marcelo Martinelli's lecture, we will have the group picture. So it means when the lecture ends, don't escape. Like one to the bathroom, one to smoke a cigarette, etc. It will take 5 minutes. We do the picture. Then you can go to the bathroom. You can go smoke a cigarette, etc. Thank you.